Hi, welcome to our presentation for Calculus 1. I am Brad Esther 2020826958 and my other teammates will be present to you about the application of differentiation. Let me introduce my team. We have Muhammad Shukri Muhammad Soeb 2020824588, Abdul Halim Iqmal 2020830526, and Nur Azira Shahira 2020460706. We will cover the application of differentiation, specifically related rates. What are related rates? Related rates are the study of mathematically that answer the problem, which is a problem we want to know one of the rates of change at a given instant. We have seen that for quantities that are changing over time, the rates at which these quantities change are given by derivatives. If two related quantities are changing over time, the rates at which the quantities change are related. For example, if a balloon is being filled with air, both the radius of the balloon and the volume of the balloon is increasing. In this presentation, we consider several problems in which two or more related quantities are changing, and we study how to determine the relationship between the rates of change of these quantities. In many real-world applications, related quantities are changing with respect to time. For example, if we consider the balloon example again, we can say that the rate of change in the volume V is related to the rate of change in the radius r. In this case, we say that dv dt and dr dt are related rates because V is related to r. Here, we study several examples of related quantities that are changing with respect to time, and we look at how to calculate one rate of change given another rate of change. Do remember that dv over dt equal to more than 0, meaning there is increase in the volume with respect of time. Meanwhile, if it is equal to less than 0, meaning that there is decrease in volume with respect of time. Now let me show you the simplest example to illustrate how related rates can be found. And now let my teammates take over my presentation as they will cover how related rates cover the application of a real-time event.
Hello, Iqbal. Yeah. Why are you calling me in the middle of the night?
Hello boss, I want to tell you that the tomato soup as our product is does not enough for 100 pi centimeter cube. Maybe you thought that it's enough, but actually not. I receive many problems and complaint for other customers about our product that it does not enough for daily user. Not only that, the customer said that they want more. In this case, I think the situation is hard and we're gonna face a big problem. So, how we gonna solve this problem, boss?
Really? I thought 150 pi centimeter cube is enough for them, for daily users, I guess. Yes. Listen. I can add up the quantity of the tomato soup up to 250 pi centimeter cube, but here's the deal. The cost of making the can of the tomato soup will increase. Yes, that sure will be. Iqmal, my best employee, can you do me a favor? Can you please find a solution on making a surface area of the can as small as possible so that the cost will be cheaper?
Hey boss, wait a minute. I think I know someone who able to solve this kind of problem. She's my friend. Her name is Shah. She is very experienced in facing this kind of our problem. Maybe she can help us to solve this problem? Who knows?
Yeah, alright Iqmal, I believe in you. Okay, good night.
Alright, boss, I won't let you down. Hello, Shahira. My boss told me that we need to figure out how to increase the quantity of the tomato soup with low cost of making the can. So, Shah, can you help me to solve that problem?
Thank you, Ekmal and Shukri. Now we know that there is a mathematical problem there. It's actually about related rate. So let me state what is the problem. A manufacturer wants to make a cylindrical can to hold 250 pi centimeters cube soup. Find the dimensions such that the surface area is small as possible so that the cost of the can as low as possible.
Here's the solution for the problem that's stated just now in the question. The volume of the tomato can is stated, which is 250 pi centimeter. The formula of volume for cylinder is pi r square h. Then we substitute the volume of the can into the formula, as I shown here. After that, we solve the equation to find the height, and the h is 250 per r squared. Next step, we find the area of the tomato can. The formula of area cylinder is 2 pi r squared plus 2 pi r h. Then we substitute the h that we found just now into this equation. And the answer for this equation is 2 pi r squared plus 500 pi over r. After we found all the information about the tomato can that we need, we differentiate the formula of area, which is 4 pi r minus 500 pi over r squared. The a over the r is equal to 0. Then we substitute the dA over the r into the equation. Next, we solve the equation to find the constant r, and the radius is 5 centimeter. After we found the r, we substitute the r into this equation to find the h, and the h is equal to 10. Next, we need to find the minimum surface area. For this step, we need to take a differentiation, which is 4 pi plus 1000 pi over r cubed. After that, we substitute the r into the equation. At r equal to 5, the answer is 12 pi centimeter. 12 pi is bigger than B0 value. Therefore, area of the tomato can is minimized when radius equal to 5 centimeter.
Now we are at the last part of the presentation. The conclusion is the reason we use related rate is simply that after doing all these derivatives, we need to be reminded that there is really an actual application to derivatives. Sometimes it is easy to forget that really is a reason that we're spending all this time on derivatives. This is our references. You can see there's a lot of references we used for this video. Thank you for watching from group 2.